All right, good morning. It's day 6 of the probability unit, and we're going to be looking at the multiplication rule of probability, or sometimes called the product rule of probability. So from the day before, the addition rule for probability was that if you're trying to calculate the probability of A or B, also A union B, you can use those both. It's the idea that probability of A or B is equal to the probability of A plus the probability of B, and then minus if there was any overlap. So that's the probability of A and B. And then using symbols, just to remind you, that's the union one. This would obviously all stay the same. Oops. And then and is the intersection. So it's the upside down U. It almost looks like an A if you were to put like a little bar across it. All right. And then over here, if A and B are mutually exclusive, that means there is nothing in the overlap. So you wouldn't have to do the last subtraction piece. In that case, it would just be the probability of A plus the probability of B. Done. All right, so it's even easier. But a lot of times there is something in the overlap, which is why we have to include that. And it says we're going to discuss the multiplication rule for probability, which is used to determine this little guy right here. So it's saying in the last class we saw the product test for independence. All right, so the test for independence was the idea of the probability of A given that B happened. Is that the same as just the probability of plain old A all by itself? All right, but we had to figure out, well, how do you calculate this conditional probability? So that's probability of A and B over the probability of B. And then is that the same as the probability of A? And then we did that last little step to cross multiply and said, hey, that ends up being probability of A and B comes out to be probability of A times the probability of B. So what it loosely turns into is if it's or, you're adding. If it's and, you're going to multiply those probabilities together. So that's kind of like the short way to remember it. Right? And it's saying, this means if A and B are independent, we can figure out that to get the probability of A and B, we're just going to simply multiply the individual probabilities. So I think at the start of yesterday's notes, we looked at like the probability of picking like the red cube out of the bag, and we found the individuals. And then what we would have done is just multiply those individual probabilities together. All right, but you'll see that in today's notes. It says, what if A and B are not independent, or what if they're dependent on one another? So in that case, what you would do, and I don't want you to overthink this one too much, but in that case, if I think that if the probability of A and B, the probability of A times the probability of B when they're independent, then all we would change for this is, let's say they're not independent or they're dependent, then the probability of A and B, you're still going to use, let's say, the probability of A, but then the second part will just change a little bit. What's the probability of B given that A has happened? But this is when the events are not independent or they are dependent. All right. So down at the bottom, when it says if A and B are independent, then it's simply going to be that the probability of A and B will be that you multiply them separately. Done. If they're not independent, then the probability of A and B would be the probability of A times the probability of B given that A has happened. Now, keep in mind, we could rearrange this. We could say the probability of B and then times the probability of A given that B happened. So don't get hung up on the order, because we know and is interchangeable, kind of like multiplication is commutative. Same thing here. Let's think about our friend the spinner. If we spin more than once, are the outcomes independent or dependent? Right? They're going to be independent. Again, don't overthink it. Don't worry about like, oh, but maybe it started on 3, so it's going to land here. No. All right. It's just equal chance of landing anywhere regardless. All right. So there's an equal chance of landing, I'll say anywhere, on spin 2. All right. It has nothing to do with spin 1. What is the probability of spinning an even and then spinning a 7? All right, so spinning and even and a 7. So it's pretty shorthand here, but hopefully you get it. Since we said that they are independent, that's just going to be the probability of spinning an even times the probability of spinning a 7, right? So think about it. Even, you got 2, 4, 6, 8. You have a 4 out of 8 chance there. Probability of spinning a 7, well, there's just one 7 on the board out of 8. And now we know we're just multiplying those together. Could you simplify that first? Of course you could. Otherwise, 4 out of 64, either way you do it, it'll come down to be 1 out of 16. So there's the chances that in 2 spins, you would land on an even on one spin and then a 7 on the next spin. So part D of the question says, what is the probability in 2 spins that you spin a 7 and an even? So it's not specifying the order, which means we could be talking about an even and then a 7, or a 7 and then an even. So in this case, what we need to do is add together those 2 probabilities, because we're really saying probability of 7, then an even, or probability of an even, and then a 7. So it's a 1/16 chance for each part. Add it together, we get 2/16, or we can reduce that down to 1/8. So you have to get a little crafty with some of those. All right, this next one, if we take a look, says, suppose a power generating facility has 3 primary safety switches in case of an emergency. The probability that any one of these switches will fail is 5%. What's the probability that all 3 of them fail, given that the switches are independent of one another? All right, so the fact that they're independent makes it nice and easy to deal with. So what we're looking at is what's the probability that the first switch fails and the second switch fails and the third switch would fail. It'd be unfortunate. So when we're saying and in between each one of them, and we know they're independent, then we're just taking the product here. So the probability of, a fail times the probability of another fail, and then times the probability of the last fail. Since each one is 5%, we can think of that as 0.05 times 0.05 times 0.05, or 0.05 raised to the third power. So grab our calculators here. Let's see if we do, lighten that up a bit. There we go. 0.05 and then raise that to the third power. We're going to get scientific notation. So 1.25 e to the negative 4th. You got to remember what that means. That means times 10 to the negative 4th power. So if I take that decimal and shift it left 4 places, let's see, it would back it up 1 and then enough for 1, 2, 3 zeros there. It'd be a very low probability, which is exactly what you want. You wouldn't want all the switches to fail at the same time. So the chances that none of them would work, right, or that they would all fail, super, super low. That's a good thing. All right, you got one last one on this page. Let's slide it up. It says, suppose that a credit card company states that when a customer is selected at random, the probability that the customer pays his or her bill in full each month is 0.35. Probability the customer makes regular online purchases, there's no shock, 0.83. And these 2 events are independent. All right. What is the probability that a randomly selected customer pays his or her bill in full and makes regular online purchases? If we see and we know they're independent, we're just simply taking the product. All right, so the probability of paying their bill in full is the 0.35. Probability of making online purchases is the 0.83. And so again, we can just use our calculator here. So 0.35 times 0.83, that'll give me 0.2905. So that's the probability you'd find somebody that does both. Okay, what's the probability that a randomly selected customer pays his or her bill in full or makes regular online purchases? All right, this goes back to what we did yesterday. So a couple things. When we see or, we should be thinking that we're adding, but we have to think of when we say like A or B, that we're going to add together those two individual probabilities and then subtract anybody in the overlap. I bring that up because in part A, that would be our paying the bill, so 0.35. Add that to anybody that shops online. But there's a lot of people in both categories. There's almost 30% right here in both. So then minus 0.2905 right there. So 0.35 plus 0.83, that would have been over 1, which would have cued us into something's wrong here. So 0.2905 off of that, we're left with 0.8895. So the chance that you would pick somebody and they would do one of those things is pretty darn high. So almost 89% of their customers fit into at least one of those categories. We've got 13 girls, 11 guys. 3 lucky students will be randomly selected to go on a math field trip. Woohoo! To spend the day with the New York Yankees statistician. Actually, that would be very cool. What is the probability that only girls are picked? Right, we have a couple more girls than guys, but still the chance that only girls are picked, right? It's definitely not going to be, 100% of the time. And it says we need to answer some questions before we can actually start that. Okay. What are the 3 events that must happen? Well, that means you would pick a girl first, and then another girl, second, if you will, and then another girl third. All right. So picking a girl and picking a girl and picking a girl. All right. The reason we draw this out, you need the ands in here. So, and it says, are these events independent? Why or why not? Well, think about the probability of picking a girl the first time. There's 13 girls to pick from. Out of this would be 24 total. If you pick the first girl, you can't pick her again. So as soon as she's out of the mix, the probability of picking a girl the next time, it now changes. It would only be 12, and there'd only be 23 students. So if the first event happening then changes the probability the second time it would happen, or for the second event, that's the definition of events being dependent on one another or not independent. So when it says, are they independent? The answer would be no, right? And because what we just said, right? Because once a girl is chosen, she can't be picked again. I'm going to use a little ... Therefore, the probability changes. Right. So when it says use the multiplication rule to determine the probability of only girls being selected, I don't want you to get all crazy fancy with the writing. Right? But on the first page, we had said, all right, if they're not independent, then the probability of A and B, you're going to do the probability of the first thing, but then times the probability of the second thing, given that the first event has occurred. So all it means is we're just going to change this number, right? Could I write it using all the fancy notation? Sure. Super not necessary, all right? So the probability of, girl number 1, I know that didn't make sense the way I wrote that, but would be 13 out of 24. The times the second girl, all right, now it's going to change a little. It's not going to stay 13 out of 24. It's now going to be 12 out of 23. And then times the probability of, girl number 3. Well, now there's only 11 girls to pick from, and there's only 22 kids to pick from. So that's all that means, is that you have to realize, like, oh, hey, it's going to change. It's not just the same thing times itself over and over again, all right, like it was in the switches question. All right, so we got 13 times 12 times 11. So our numerator, let me move that out of the way, 17, 16. Our denominator, 24 times 23 times 22 over 12,144. Now, of course, this thing will probably simplify, so divide it, and then math frac, and that comes down to be 13 out of 92. So as a quick reminder, don't forget when you're multiplying fractions, you multiply the top together, the bottom together. You can do it all at once on the calculator. You choose, all right? But that's the chance that the first person would be a girl, the second person would be a girl, and the third person would be a girl. All right. How can we determine the probability of at least one boy being selected? Right? If you think about it, if that's the chance that it's all girls, then every other scenario has to have at least one guy in it. It might have one, it might have two, it might have all three. So think about if that's the case of all girls, and they figure out every other case, well, all the cases total should add up to 1. So if I want to find the probability of at least one boy, it's 1 minus the probability of all girls. So 1 minus 13 out of 92 is going to leave us with 79 out of 92. There you go. So sometimes you just have to get a little crafty and thinking like, how would I calculate this? Rather than trying to calculate all the cases where there's 1 boy and then 2 boys and 3 boys and add them all up, just take out the cases that don't have any guys in it. All right, last page of notes. We're back to a bag of marbles here. We got 12 red marbles, 8 blue, 5 green. It's saying if 3 marbles are pulled out, find each of the probabilities. In each, we specify either replacement, that the marbles go back, or no replacement. So you have to think about how does that affect the independent versus dependent kind of status there. Oops, sorry. So it says find the probability of pulling 3 green marbles with replacement. So you pick it up, you're like, hey, look, it's green. You put it back in. So this next time you go to pick out another marble, the probability isn't going to change. So because you're replacing it, that means that they're independent. All right. So that means when we want 3, you're just going to take the probability of green, probability of green, probability of green, and the probability does not change one bit. So it's 5 green marbles out of, that would be 25 total. And then same thing here, 5 out of 25, 5 out of 25. And so you can, of course, reduce each one of those to 1/5. And so then 1/5, oh, we don't even need a calculator. 1/5 cubed. 1 cubed is 1, 5 cubed is 125. So is it a high chance? No, it's less than 1% right there that you would, assuming you're not cheating and you're not looking, that you'd pick out a green marble each time. All right, find the probability of pulling out 3 red marbles, but without replacement. All right, so if I don't put the marbles back in, each time I take one out, there's less marbles in there, which means these are not independent or they are dependent events. So you just have to remember the probability is going to change here. Now, technically, we could say like probability of red times the probability of red given that the first one was red, probability of red given that the first, 2 are red. Do you really need to write that down? No, just think about how the numbers change. So the first time chance of getting a red marble, there's 12 of them out of 25. The next time you took out a red marble, so there's only 11 in there, and there's 24 total. You kept that one. Now there's only 10 out of 23. So don't worry about this part. Focus on that part, all right? And then multiply it all out. If you trust my calculations, which I hope you do, would be 1320 over 13,800, and that'll reduce to 11 out of 115.